Hello, everyone. Good evening.
Good evening, ma'am.
Yes. So today we are going to do week 7. So did you watch any lectures?
Yes, ma'am.
Yes. How is it? Okay, many people are saying no.
It was easy, ma'am.
Easy. Okay. Yeah.
Simple statistics like
Yeah.
status one.
Yeah. Like statistics one. Here in this week we have talked mostly about descriptive statistics part. So you have all the sample mean, sample variance. And we have one more statistics that we have talked about here. That is sample proportion. Yes,
Ma'am,
Vishnu. Hmm.
ma'am, in my extra activity 3,
Hmm.
second period is giving bad numbers. I don't know. When I solve everything which you have asked in extra activity.
Yeah, so such cases, we had announced it in the starting itself that such cases is going to be taken care by us. So if let's say you are like two of your peers have given you very good marks and another peer have given you straight zero, then for sure such cases are going to be looked into. Or even if some peers have given you 100 and other peers have given you like 30, such cases will be taken care of us, so don't worry about it.
That type, yes.
Yeah. Yes, Tisha.
Ma'am, I received only one peer review. Two are not given.
Yeah, even such cases will be taken care by us, Tisha. Don't worry.
Okay, ma'am.
Hmm.
Ma'am, same
And
happens
and
with me,
ma'am,
ma'am.
Yeah.
ma'am,
So
on
if the peer review is not complete, such cases will also be handled by us.
No,
and
ma'am,
ma'am,
actually,
Bhumika, go.
another doubt
Okay.
is how many extra activity are more.
There are total of I think 5 to 6 extra activities.
Okay.
Yeah. Yes, Bhumika.
ma'am, same happens with me, ma'am. Like the two peer reviews are there, and they have written like all things are present, but they are giving me 85 and 95. So I don't know why this.
Uh, yeah.
They have they themselves have written comments like all things are present, and but
Maybe some explanations are not very good. Things like that might happen. So that is why you might not have gotten full marks.
ma'am, I have written all things, and I don't know why.
Hmm. Yeah, but we cannot check everything. Like you're saying 30, 95, 85. So that doesn't look like some extreme cases.
So in my case, first period is giving 95 and second period is giving 55.
Such cases will be taken care of because it's quite big. Priyanshu, you have anything?
Yes, ma'am. I wanted to check what we are going to cover today.
Okay. So today we are going to do week 7. Um,
Concepts?
week 6? Week 6 is done, right?
No, no, ma'am. I mean concepts
Oh,
of week
yeah,
7.
we'll cover the concepts.
Okay, ma'am. Thank you.
Ma'am,
Just try to. Okay, Kiran, yes, go ahead.
what if we miss any extra activity?
If you miss any extra activity, that is not a problem because, anyways, it's something apart from your coursework. I mean, it is extra 5 points that you get if you do it. If you miss one of it, maybe you lose some marks. And I think we take some best 4 out of 5 or something. I'm not very sure, but I think that's
There
the
are
case.
six. And
Even if it's not best 4 out of 5 or best 5 out of 6, yeah, someone is saying best 4 out of 6. Yeah, it is. You'll be fine.
Ma'am, could you please solve one question from week 5 at last tutorial? One last question.
Week 5.
Yes,
Yes,
ma'am.
ma'am.
Ma'am,
Ma'am, you
I
said
asked.
that.
asked many times.
Can you repeat? What did you say?
Ma'am, week 5 tutorial 1, last question. Could you please solve at last?
Hasn't this been covered in TA session? I had
No,
mentioned
ma'am.
this to be covered.
No, ma'am.
This session will not do week 7. Maybe, okay. If it's not been done, I'm sure it would have been done, that question. Last time I
Ma'am,
told
you
it would be done with TA session.
Ma'am, yes, ma'am, but it's not discussed.
Okay, but right now we won't be doing it. Okay, let's see if there is time at the end. We can go there.
Okay, ma'am.
Hello, ma'am. Excuse me, ma'am.
Yes, Jyotif.
Yeah, ma'am. I am asking that week from 7 to week 12, shall we get different things? Means, ma'am, I have not watched. Is week 7 relate concepts are means week 6 and week 5 and 6? Okay, ma'am. I have not done week 5 and 6. So, shall the concepts of 5 and 6 will apply in this week 7?
Yes, not very much, but you should know how to solve the probabilities. All the joint, marginal, everything you should know.
Okay, ma'am. Thank you, ma'am.
Ma'am,
Hmm.
can a joint density be greater than 1?
Yes, densities can be greater than 1, no?
Okay, but then
They're not
margin
probabilities.
should be okay. Marginal should be in between 0 and 1, right?
Are you talking about marginal density or probability?
Yeah, marginal density.
It can also be greater than 1.
But we do integration. It should be. It is a probability we are finding fx of x. So marginal should be less than 1.
No, fx is marginal density, no?
Yeah, marginal density is a probability.
No, it's a density, right? When you're saying, let's say if you're talking about one random variable, what is PDF? It's density,
PDF
no?
is a,
Probability density function.
yeah.
Ma'am, can you tell what is the difference between sample and sampling?
Yeah, we'll start week 7, just maybe in a minute or so.
Okay, ma'am.
I see that like many of you are asking week 5, 6. So maybe we can arrange one more session where we can discuss week 5 and 6. Like if you have any doubts from week 5, 6, we can take in that separate session. So today's session, let's stick to week 7 part. Any doubt from week 5, 6, we'll take in the other session.
Okay, ma'am.
Ma'am, are you doing a PhD or?
Maybe we can do it after the session. No, I'm not doing PhD. All right.
or any training,
Mhm.
or any kind of training or internship?
Maybe we can discuss it later.
Okay.
Right. So today, many of you had OPP, is it?
Yes, ma'am.
Yes, ma'am. Yes, ma'am. It was very tough.
Very tough. Python.
Yes, ma'am.
Yeah, ma'am.
Yes, ma'am.
I I don't know how to clear in next time. Maybe I need 2 3 term to clear OP.
Maybe you can practice more. Okay, let's start week 7. So the topics that we have here is we are going to look at IID samples basically, and in IID samples, we're also going to, when we talk about IID samples, we're also going to see what do we mean by sampling and sample, like what's the difference between them. Then we will also talk about uh, expectation of, we'll talk about empirical distribution. Okay. Then we will talk about descriptive statistics. Some descriptive statistics on the sample. So some of the statistics that we're going to look at is one is our sample mean. Then next is sample variance. And next is sample proportion. And for each of these statistics, we are going to look at expected value of sample mean and variance of sample mean, like their expectation and variance we are going to look at for each of these statistics. Once we see all this descriptive statistic, then we will move to sum of random variables. Okay. After that, at the end we'll look at weak law of large number, which is nothing but Chebyshev inequality. All right. So IID samples, we have seen it before, right? When we are talking about, when we were in, I think, week 3, we had looked at IID samples, or week 4 somewhere. So first question is, what do we mean by IID samples?
Independent and identically distributed.
Independent and identically distributed. So when we write, x1, x2, so on till xn is IIDX, right? So what does it mean? It means that all these xi's are independent and they all are coming from the same distribution as x. Okay. So even xi is coming from the distribution x, x2 is coming from distribution x. So until even xn is coming from distribution x. So what we are what we are going to do in this chapter, like from this chapter onwards, is like given this, I mean, you have some samples coming from a population, and let's say you are not, you don't know all the parameters that are there in your distribution. Maybe, let's say, I just know that my samples are coming from a Bernoulli distribution, or my samples are coming from a normal distribution or coming from exponential distribution, right? But all of these distribution has some parameter associated with it. Like if I'm talking about the Bernoulli distribution, we know that there is a parameter P, which is the probability of success. If I'm talking about the Poisson distribution, if I'm saying that my samples are coming from this Poisson lambda, so this lambda is the parameter associated, right? If I'm talking about the normal distribution, so again here we have two parameters, mu and sigma square. So, let's say we have just some idea that okay, we have these samples and they are coming from such particular these distributions, let's say, but we may not know what the parameters are for these for these distribution. So how do we estimate it? How do we like uh, find out, or even like not exactly, maybe we'll just try to estimate those parameters using those samples. So this is how we are going to start from week 7 onwards. So we'll look at like what the sample is and how does it, how does a sample look like coming from different distributions, and how do we find the sample means or different statistics on those samples. So what are we trying to do here? So what we're trying to do is you have some IID samples given and you want to get some more information about your distribution. Let's say you want to, getting some more information means you may want to find these actual parameters, like what are these parameters. Now we'll understand this more using some examples. Let's say I have
Ma'am, you are writing.
my screen is not visible.
Ma'am, screen is visible. Only XI, XIJ are independent. That part is visible.
Not sure why is it. No, I have written something more. Maybe I will reshare. Is it visible now?
Yes.
Yes, ma'am. Visible.
Yeah. Okay. So we'll understand this using some examples. So we'll take a very simple. We are starting very simple example. So suppose that you have 20 IID samples, or let's say 10 IID samples. So X1, X2 up to X10. They are IID coming from Bernoulli P distribution. Okay. We don't know what P is. Okay. Here P is not known to us. P is unknown. Let's say we have generated, we have obtained these samples from some Bernoulli P distribution, and they have been taken independently, and they all are identically distributed as Bernoulli P. They all are coming from the same Bernoulli P distribution. Okay. So we might, like for different instance, we might receive different samples. So let's say I give you 10 sample, 10 IID sample right now. So I might get something maybe 110011 0 0 1 0. So this is a particular sampling instance is what we will call as the sampling. So I mean, we are generating samples from Bernoulli P distribution, but every time at different point of time, or every time, maybe you have some random number generator, and every time you redo it, it gives you a different sample, right? So the actual instance of the sample, these are called the samplings. So these words, we are not going to use this sampling anywhere later, but any particular instance of the sample, we are just calling it as sampling. So this is my sampling one. Let's say again we Yes, Priyanshu.
Ma'am, can you please explain when you say sampling instance, are you referring to this one
Uh, this
or are you
whole
referring to
thing.
X1? So this whole thing is called as sampling.
Yeah, I mean a particular instance of the sample. I mean x1, let's say these all are random variable, right? X1, X2, X10, all are random variables,
Mm-hmm.
right? And
So
each
X1
of
is
these
one of the
x's,
sample.
are coming from Bernoulli P. So maybe, and since this is random variable, every time it can generate different values, right?
Yes,
So
ma'am.
maybe at this point of time, my x1 gave me 1, x2 gave me 1, x3 is 0, x4 is 0, x5 is 1, x6 is 1, and so on. So this is one sampling. Now I can give different sampling also, right? My x1 can take, let's say again 1, x2 0, 1, 0, 0, 1, 0, 1, 1, 1, something like that, this, right? So this is another sampling. This is, let's say, sampling 2. And it will keep on
Yes.
going. So any particular instance of the sample, you just name it as you just call it as sampling.
Got it, ma'am. Thank you.
Yeah?
Ma'am, why we need sampling?
We don't, I mean, see, you're not going, like when you are dealing with the data set, I mean, you are just going to get one particular sample. So that is just one sampling instance. We are not going to, and we are not going to tell you that this is called sampling. I mean, in general, all of this has been called as samples only. But actually, like when you move forward, right, you will see that one sampling is being given, one sample is there, right? So we'll just write it as x1, small x1, small x2, small x3, so on to small xn. This is one sample that we got. This is just a terminology, the sampling, right? Just a terminology. Like at different point of time, you will receive different samples. That's all.
Okay, ma'am.
Yeah. And what we are saying is, like, all these samplings have been generated from for the same P. I mean, P, it's not that, since they are all IID, so P would be same. For every sample has been generated from the same Bernoulli P. Okay. Then, given this IID samples, what we want is, we want to know what is the empirical distribution, right? So what is called the empirical
Ma'am,
distribution?
what is the meaning of empirical distribution?
Yes, I'll go there. Let me just try it. So we are going to find something which is called the empirical distribution.
Ma'am, can you increase the font size?
Can I
Increase the font size.
increase the font size? Or maybe I will write a little bigger. It's okay.
Ma'am,
Hmm?
so the concept of sampling, it is arbitrary and it can be present in all types of distributions, right?
Yes, yes.
Okay, ma'am.
This font size is fine.
Yes, ma'am.
Okay. So what we are saying is, suppose you have x1, x2, xn. They are IID x, let's say, and us. Okay. So when we when we want to find the empirical distribution, so how do we define it? Is probability of t is equal to number of times that xi is equal to t divided by n. So what does it mean is, so let's say you have the samples, x1, x2 up to xn. They all are coming from IIDX. Now, if you want to know, like now in your samples there will be various values, right? And if you want to know what is the distribution of all these values, then how do you what are the probabilities going to be? You're finding the distribution for this sample. So for example, if I want to know that, so probability of t means what? In the sample, what is the probability of t, right? So that is nothing but number of times that observation t has occurred in the sample divided by the total number of observations that you have. So
Ma'am,
if
what
you
is
go,
the meaning of hash here?
yeah, that is just number of times. We will write number of times t appears in the sample divided by n. For example, let's say I have x1, x2, x10, IID, Bernoulli, P. Okay. So the sample that we got, let's say it's 1 1 0 1 0 1 0 0 1 0. Okay. Now you can see that in this sample you have a 0 and a 1, right? So what is the probability of 0? It will be number of times 0 appeared in the sample. So how many times 0 appeared in the sample?
Ma'am, 5 times.
5 times. And what is the total number of observation?
10.
10.
1 by 2.
So probability is 1 by 2. Similarly, what is P of 1? That is again 5 by 10.
Yes, ma'am.
Right? So if I have to write the empirical distribution of the sample, what will I write? I will write as, so you have, okay. So you have some t, and t is 0, 1. And what is the P of t? This is 1 by 2, 1 by 2. So this is the empirical distribution, right?
Yes, ma'am.
Very easy. I mean, any given, if you're given some sample, some IID samples, then you can easily find the empirical distribution. Yes, Abhinash. Arpit.
How is it different from PMF table?
Yeah, sorry, can you repeat?
How is it different from PMF table?
How is it different from PMF table? So, okay. In the PMF table, I mean, the probabilities are given to you, no? I mean, we are not saying, there we don't give you that, okay, my x takes the value 0, 1, and how many times, there you don't know how many times your 0 has come or how many times your 1 has come. We are just saying that, suppose you have a random variable x and it takes the value 0 with this probability, and it takes the value 1 with this probability. But here, depending on what you have observed your sample as, from there we are calculating the probabilities. So this is the empirical distribution which you are calculating from the samples.
Ma'am, it seems to be similar to Monte Carlo simulation.
Yeah, similar to Monte Carlo simulation. Yeah.
But for Monte Carlo simulation, we say it's equivalent.
What is equivalent?
I mean, instead of equality sign, equivalence is shown.
I think approximately. I mean, we say approximately this.
Approximately equivalent.
Yeah. Okay. So this is, so given any sample, you should be able to calculate the empirical distribution. Now, after empirical distribution, what we want is, we want to see some descriptive statistics of the sample. Right? So now, given this sample, let's say this is one sample, right? Now, let's say I want to find out what is the sample mean. Just want to calculate some statistics, right? So what is the sample mean of this? What is the sample variance? And what is the sample proportion? So before we calculate all these, we'll go and just define what these statistics mean. Okay. So the setup is again the same. We have some IID samples, let x1, x2 up to xn be IID samples. They're IID x. Then what we say is we call x bar, which is a sample mean. This is equal to x1 plus x2 plus up to xn by n. This is what we call it as sample mean. So this sample mean is not a constant. This is a random variable. Why is this a random variable? Why is sample mean a random variable?
Because sample is random and are not unique.
Yeah. So for
there are many instances.
Yeah. For different instances, you will get different samples, and accordingly, your sample mean will also keep on changing, right? So this is a variable. This is a random variable.
And the distribution mean must be constant.
Distribution mean will be constant. Yes. So if, let's say, in this example, if I'm saying that x1, x2 up to x10 is coming from Bernoulli P, then what is the distribution mean? What does the distribution mean in this example?
P.
Distribution mean is P, correct. And what is the sample mean? What is the sample mean?
Ma'am,
5 by 10.
5 by 10. There's nothing but 1 by 2.
Excuse me, ma'am.
Yes.
Yeah, ma'am. Distribution mean I didn't get. Means distribution mean can't be a integer. It's always a variable or what, ma'am?
Distribution mean. Okay.
Yeah.
Okay. See, we had the samples coming from Bernoulli P. So when we are saying distribution mean, it means the distribution is, in this case, is Bernoulli, because my samples are coming from Bernoulli distribution. And what is the parameter? It is P. And we know that if you have, if you are given a random variable which follows a Bernoulli P distribution, then the mean of that random variable is going to be P, right? So that is why we are saying that the distribution mean here is P. Now, for example, let's take another example. Let's say my x1, x2, xn, they are IID with normal with mean 0 and variance sigma square. So what is my distribution mean here in this case?
0.
Distribution mean would be 0. Because all these samples are coming from a normal, they all are coming from normal with mean 0 and variance sigma square. And I know that if I have any normal distribution with mean mu and variance sigma square, then my mean is mu, right? So my distribution mean is mu, which is in this case is 0. Sample mean you will calculate from the sample. So your distribution mean is constant, but your sample mean is a random variable.
Can you explain about distribution mean again? I didn't understand.
Okay. So what do you understand by distribution, first of all?
It is the spread of a particular value.
Spread of a particular value. You have heard of Bernoulli distribution, binomial distribution,
Yes.
Poisson distribution, right? Right. So what we are saying is, suppose my samples are coming from Bernoulli P distribution. Okay, Bernoulli distribution it is coming from. So we have written one sample here, which is this, right?
Yes, ma'am.
Correct. So writing this means what? That my samples, the samples that we have generated is from Bernoulli P. It means every random variable here, x1, x2 up to xn, they all are following the Bernoulli P distribution. Okay. So if my distribution, if my sample is coming from Bernoulli P distribution, and I know that the mean for this this Bernoulli P is P, so we are calling the distribution mean as P. Now, let's say if my samples are coming from normal with mean mu and variance sigma square. So if the samples are coming from a normal with mean mu and variance sigma square, then we know that for this distribution, for normal distribution, my mean is nothing but mu here. So this is my distribution mean, which is mu.
Yes, ma'am.
Okay, you got it?
Yes, ma'am.
Okay.
Ma'am.
Excuse me.
Ma'am, here sample mean is actually of 0 and 1, both are 5 by 10. But if in case, like if it is different, so what will be the sample mean?
It will be different. Let's say let's say now you have, suppose this as 1. Then what happens? Your P of 1 becomes 6 by 10 and P of 0 becomes 4 by 10. That's all.
So sample mean will be both like 4 by 10.
No, what is sample mean? Sample mean is defined as this, no? You add all this is the empirical distribution, okay? So sample mean is nothing but just 6 by 10, because when all the samples are coming from just the Bernoulli P distribution, this is for a particular example I'm talking about, okay? Bernoulli distribution I'm talking about. So when all these samples, x1, x2, that we have written here, x1, x2, xn, if they all are coming from Bernoulli P, it means they all are taking the value either 1 or 0, right? Correct?
Yes,
they all are taking the value either 0 or 1. Now, if I define the sample mean, this is nothing but x1 plus x2 plus up to xn divided by n. So when it is a Bernoulli distribution, then you will get either 0 or 1. So when you add everything, I mean, zeros are just going to get discarded, no? So what will be the sample mean in this case? Can you tell me?
6 by 10.
6 by 10.
Ma'am, here is 6 by 11 and 4 by 11 now.
Is it 11 values?
Ma'am, you add one more value.
No, ma'am, it's 10 only.
It's 10.
It's 10 only. I mean, I didn't add. I removed one. And I added one. So it's still 10.
Okay, ma'am.
So sample mean is 6 by 10.
Ma'am?
Maybe, yeah.
Ma'am, in this case, on the sample proportion of 1 should be equal to the sample mean, right?
Sample, we have not yet seen the sample proportion definition. We'll come back to that.
That means P of 1 should be equal to sample mean. For
sample proportion, let's first see the definition, because I have not discussed it just for now.
Okay.
Yeah. So given any samples, you should be able to find the sample mean.
Ma'am, is there any relationship between distribution mean and sample mean?
There is no such relation, but what
or if we want to understand which one will always be greater than other. So in this case, if I have to infer that which one will be greater, distribution mean or between distribution mean and sample mean. So is there any such
see, first of all, you don't know what is your distribution mean, right? You don't know. You're just trying to estimate it using the samples. You don't know exactly what your distribution mean is. So what we can do is maybe we can just find like how close my sample mean and the distribution mean are. This is what we can look at. Or there are different
Okay,
ways
okay.
to
Right, ma'am.
estimate.
Because I think we say that parameters are not known, right?
Yeah, parameters
So,
are not known.
understood, ma'am. Thank you.
Yeah, only we just have some idea that let's say my sample are coming from this distribution. And from there, from those samples, we are trying to estimate those parameters. So estimation is a different topic, or maybe week 9, then become week 9, 10, we'll look at it. But right now, we just have to understand these different statistics. Okay, so in the sample mean, what if I have to find the expected value of sample mean? Expected value of x bar. So what is x bar? X bar, we wrote it as x1 plus x2 plus up to xn by n, right? And the setup was that I have my x1, x2, xn, IID x. Let's say expectation of x was mu and variance of x is given to be sigma square. Okay. We know that expectation follows the linearity property. Okay, we know that expectation follows the linearity property, right? So expectation of x1 plus x2 plus up to xn by n will be what? Since n is a constant, I can just take it out and I will have expected value of x1 plus x2 plus up to xn, right? And this I can write it as expected value of x1 plus up to expected value of xn. And since all of these random variables are IID x, so all these x1, x2, xn are coming from the distribution x, and their mean and variance is given to us as mu and sigma square, then expected value of each of these xi, I can write it as mu, right? And how many times it is occurring? It is n times. So this is equal to n mu divided by n, which is mu. So what did we get? We got expected value of x bar equal to sample, distribution mean, which is mu. So my so whatever sample mean you have, so what can we expect my sample mean to be? This is equal to the distribution mean. But what about the variance of, now we have this statistic, which is sample mean. We found its expectation. Now we can also look at what is the variance of, this x bar, right? So again, what is x bar? X bar is x1 plus x2 plus up to xn divided by n. Okay. And since they all are IIDs, I can write it separately, right? And since n is a constant, when it comes out, it will be 1 upon n square. And inside it will be variance of x1 plus up to variance of xn, right? And what is variance of each of these xi's given to us? That is sigma square. And how many times it is occurring? Which is n sigma square. So this is equal to sigma square by n. So we got variance of x bar to be sigma square by n. So what did we see so far? We had some IID samples coming from the distribution x, where the distribution of where the expectation of x was given to us as mu and variance of x was given to us as sigma square. Now from this sample, we can find the sample mean, and this sample mean is given by x bar is equal to x1 plus x2 plus up to xn by n. So this is my sample mean. Now, since this sample mean is a random variable, I can always go and find its expectation and variance. So when we found the expected value of x bar, we got this to be mu, and the variance of x bar we got to be sigma square by n. Any doubt in this?
No, ma'am.
Sample mean, the sample mean you wrote 6 upon 10. Why it is not average of 6 upon 10 and 4 upon 10?
Can you repeat? Sample mean, this example?
Yes, ma'am. Yes, ma'am.
Sample mean is?
When you mentioned 6 upon 10, then just below it.
For this example, yes, it is 6 upon 10.
Why that it is not the average of 4 by 10 and 6 by 10?
Why is it not the average of? Okay, how do you define your sample mean? What is sample mean? So since you have 10 samples here, so I will do x1 plus x2 plus up to x10 by 10, right? Now what is my x1 taking? 1. What is x2? 1. x3 is 0. x4 is 1. x5 is 0, and so on. So if I add everything, that is nothing but number of times my 1 has occurred in the sample, which is equal to 6. Yeah. This is how we find the sample mean.
Ma'am, what is the formula of sample variance?
Yeah, sample variance we are going to look next.
Hello,
Sigma
ma'am.
square by n.
No, this is not sample variance. This is variance of the sample mean. So you had, so what we saw here is you had x1, x2, xn, IID x, okay, and expected value of x was given to us as mu, and variance of x was given to us as sigma square. We found one statistic here, which is sample mean. So using the sample, this is a sample. So using this sample, we found the sample mean, which is my x bar, and it is given to be x1 plus x2 plus xn by n, right? This is my sample mean. Now, this x bar is a random variable. Now, if x bar is a random variable, and we know that if we have a random variable, we can talk about its expectation and its variance. So what did we found? What did we find expectation of x bar to be? We found this to be equal to my distribution mean itself, which is mu, and we found the variance of this random variable x bar to be sigma square by n, which is nothing but variance of x divided by n. This is equal to. This is fine. This is the result that we obtained.
Okay, ma'am.
So you can see here that in variance of x bar, you are also getting you in the denominator. You have this n. You have this sample size coming into the picture. So what does it say? Like the more and more samples you will have, the less variance you will see in your sample mean. Right? This is the observation that you can take from here.
Ma'am, how do we get sigma square here?
Sigma square is given to us. I mean, we are
Okay,
saying that,
given.
yeah. Sigma square is
Ma'am,
nothing but variance of x.
okay, and how sample variance is different from the variance of sample mean? I'm actually
This
bit
is
struggling
variance
to
of,
understand it.
this is, okay. See, this is the setup. This is the setup I have written here, right? You have, what we are saying is you have n IID samples coming from a distribution x, whose mean is given to you as mu and variance is given to you as sigma square. Okay. Now using this sample, I found the sample mean, which is x bar is equal to x1 plus x2 plus up to xn by n. This is a sample mean. Now this sample mean is not a constant. It's not a real number. It's not a constant. It is a random variable, because for every different sample we take, we are going to get different sample mean. This is a random variable. Now, if this is a random variable, I can look at what is the expected value of x bar. I can also look at what is the variance of x bar. So maybe you can, like when you're saying sample mean, you can think of it as different random variable. Maybe let's say I can call it as y. So if y is a random variable, I can find the expectation of y, right? I can find the variance of y.
Right.
Yeah. So expectation of y will give what? So where is this random variable centered? Variance of y will give what? How spread out my data is, how spread out the values are, right? That is the way what the variance give.
Yes, ma'am. Clear.
Yeah?
Now. Thank you.
So this is the first.
Excuse me, ma'am.
Yes.
This is the first. Yes.
Ma'am, could you take
Hello,
one
ma'am.
example, numerical
Hello,
example,
for
and
all type of
show us
distribution,
one.
like in this
Wait.
example, you
Raj, can you just wait? I think someone was saying something. Joydev, was that you?
Yes, ma'am. I am telling that could you take one example, numerical example, to show us expected value of that variance and mu. Just you wrote right side. Right side. Ma'am, are you understanding? I am telling just can you could you take one example of numerical? Yeah. Example.
Okay.
Numerical example.
Yes, Raj, go ahead.
yes, ma'am. So I'm saying, like in this particular situation, you took an example of binomial, I think. So is this formula of mean, expectation, and variance will be same for every type of distribution, no? Like,
Yes, every type of
or it will
distribution.
vary.
No, this will be same. I mean, I am talking about any general distribution X, right? This is not any specific distribution. It is any distribution, any general distribution you take. So whenever you have IID samples coming from any distribution, then your expected value of sample mean will come out to be equal as distribution mean, and your variance of the sample mean will come out to be variance of the distribution divided by n. This is in general. If I take, you substitute different, so maybe what we can do is, let's say I have x1, x2, x10. These are IID Bernoulli P. Okay. So in this case, my expected value of x bar would be what? P. And what will be variance of x bar? Sigma square by n.
Yes.
What is sigma square for Bernoulli? P times 1 minus P.
Yes.
Right. So this is when I take Bernoulli P. Now let's say I take x1, x2. So since I've taken, let's take it n here. Xn, they are coming from exponential lambda. Okay. So again, I define my sample mean, which is sum over xi, I varying from 1 to n divided by n, right? And I want to know what is expected value of x bar. So expected value of using this result over here, we got expected value of x bar to be, it should be equal to the distribution mean. And in this example, my distribution is exponential and it has the parameter lambda. And I know if a random variable follows exponential lambda, then its expectation, then its mean is given by 1 upon lambda. So for this example, my expected value of x bar is 1 upon lambda. What is my variance of x bar going to be? Sigma square by n. What is sigma square
Yes.
in this case?
1 by lambda square, I think.
1 by lambda square divided by
Yes.
n. So you just change the distribution here, and accordingly you can find all your expected values and variance.
Ma'am,
ma'am.
this is an example for sample mean.
Sample mean, yes, this is for sample mean. Now if I take here, let's say, a normal distribution, normal with mean, mu and variance sigma square, or maybe normal with mean 1 and variance 2, then what will be expected value of x bar?
Mu by sorry, mu
Mu is what?
mu.
One.
I
In
think
this
mu
case,
mu.
1. Yeah.
Okay. Yeah. Okay.
Variance of x bar is sigma square by n. What is sigma square?
2 sigma is
2. 2
2.
divided by n. So given any IID distribution, if you have to find the expected value of x bar and variance of x bar, this is the formula that you're going to use. That is, expected value of x bar will always be equal to the expected value of x, and variance of x bar will always be equal to variance of x divided by n.
Ma'am, in the last question, what is the value of n?
In the last question, what is the value of
N.
and n can take any value, no? N is the sample size. What is the sample size we want? N can be 10, 20, 30, 40. Depends. I mean, it depends on what sample size you want to take. I can have just 3 samples also coming in, or I can have just 2 samples also coming in. Okay.
Ma'am, for normal distribution, what is the expectation? Well,
What is the expectation of?
what is the expectation formula and for variance also?
So when you have any distribution x which follows any random variable x which follows normal with mean mu, normal mu sigma square, then expected value of x is mu and variance of x is sigma square. The first term is your mean and the second term is your variance. Right? This is how we write normal distribution.
Yes, ma'am.
Okay, let's move to the next statistic now. So the next statistic that we are going to talk about is sample variance. So what is sample variance? Again, we have, we'll say that we have this x1, x2, xn, IIDx, right? So the sample, and we found, let's say, we found the sample mean, which is sum over xi, I varying from 1 to n divided by n. We have the sample mean. Then sample variance is denoted by S square, capital S square. And this is given by sum over xi minus x bar whole square, I varying from 1 to n divided by n minus 1. Okay, remember that this is n minus 1 and not n, because we're talking about sample variance. So in stats 1, you have seen this population variance, sample variance. Right?
Yes, ma'am.
Yes,
Yeah.
ma'am.
So in sample variance, you have to, so we're talking about the sample variance. So you have to you have to subtract not the mean of the distribution, but you have to subtract the sample mean. Right? You have xi minus x bar whole square. This is x bar, right? So sum over xi minus x bar whole square divided by n minus 1. This is your sample variance.
Ma'am, what about the variance that we found before?
Variance that we found before was variance of x bar.
Oh.
Right? This is not variance of x bar. X bar was one statistic, right? And that statistic, that sample mean, was also a random variable, and that is why we were able to compute its expectation and its variance. Now, this sample variance is another statistic, and this we are denoting it by S square, right? And the way it is defined, it is this is equal to sum over xi minus x bar whole square, I varying from 1 to n, divided by n minus 1. So this is another statistic, and we can also, and this is also a random variable, because every time the sample will change, my x bar will change and your overall s square will change, right? So again,
sorry to interrupt. Why do we divide by n minus 1? What is the idea behind having n minus 1 instead of n in the denominator, ma'am?
Yeah, so week 9 is where you'll get this answer. So it is something related to biasness and unbiasedness of the estimator. So in week 9, you will be introduced to the concept of estimator, and there you will see biased estimator, unbiased estimator. So there you will see that this specific S square, like this statistic S square, is an unbiased estimator, and that is what we generally want. We want unbiasedness, and that is why this has been divided by n-1. Everything we'll look at it more detail in week 9. So S square is again a random variable. This is okay. I mean, why is this random variable? Every time your sample changes, your x bar changes, and you will get different set of values for S square. This is fine.
Yes, ma'am.
Yes, ma'am. You can proceed, ma'am.
Okay. Now, yes. Yes, Raj.
Yes, ma'am. It's a little doubt. Like in exam, if they'll ask about variance of sample, so then what I'll
Variance of?
consider,
So,
to find a variance of sample, something like that.
why would variance of sample you're saying?
Yeah, as you explained, previously, not that much previous,
Yeah.
where you are explaining currently.
Okay.
Yeah. So here, here you are explaining about sample variance. You gave us a formula for it,
Right.
and just before it, you explained x bar variance of x bar.
Variance of x bar, yes.
Yeah. So I'm getting little confusion between both of it.
Yeah. Okay.
I'll differentiate with what I have to find and what I haven't.
Okay. See, so in the previous example, so what I said is we are computing various descriptive statistics, right?
Yes.
So we are looking at various different statistics, where one of the statistics was, my first statistics that we introduced is sample mean, which was denoted by x bar. For this x bar, which is a random variable, right? So x bar is a random variable. So in when you were in week 3, for any random variable, you found the expectation, right?
Yes,
You
ma'am.
found the expectation of random variable, expectation of random variable, and you also found the variance of random variable, correct?
Yes, ma'am.
So here also this x bar is a random variable, right? So if x bar is a random variable, I can find its expected value and I can find its variance. So let's say maybe my x bar follows, let's say, a normal distribution, okay? assume that my X bar follows a normal distribution. So this is the distribution of X bar, okay? Which is, let's say, this is following normal with mean mu and some variance sigma square. So what is going to be expected value of X bar? Mu.
Yes, ma'am.
And sorry, not that. So when we are saying expected value of X bar, it means that my X bar is centered around mu. And the variance of X would give you, like, what is the spread of this random variable? How much spread it is around the mean? That is what give you the variance, right? So this is variance of X bar. So for this random variable X bar, you are computing the expectation and you're computing the variance, right?
Okay.
And this variance, what you have also got is this variance of X bar would be sigma square by n. So as your sample size would increase, you would expect that your variance of X bar would keep on decreasing. So if my sample size was, let's say, 10, so let's say for n is equal to, let's say, or maybe 100, or maybe I'll start with 50. So let's say this was the variance. Now, if I increase the sample size, let's say I take 100 samples, and now the distribution of my X bar looks like this, or this is not fine. But this is my mu, and now my variance would decrease, no? Because this is what we would expect. Because this is what the formula also says, that the variance of this X bar should reduce as the sample size increases.
And
so
the
now
height.
you can see that when n was 50, the spread was more. Now when n is 100, the spread is less, right?
Yes, ma'am.
Yeah. So this is variance of X bar. Okay.
Ma'am, logically speaking, why the spread is reduced? Apart from the formula, could you please try helping me understand?
Without the formula?
Yeah, without the formula, what is the logic behind shrinking of the spread?
See, okay. Before you had, let's say if I'm talking about, if I just take 5 samples, and these samples, let's say, are coming from a normal distribution. It is very likely that most of, and you know, if it is a normal distribution, it can take values anywhere from a minus infinity to infinity.
Okay, ma'am. So,
Yeah.
okay, now I have another question. If we have infinite sample, then the variance becomes 0, is it?
Your sample would not be infinite, but as you, I mean, the more the sample sizes, the better it is. You will get a more clear picture of what is, I mean, you would expect most of the sample to be around your
mean
expectation. Yeah, mean.
Around the mean. Okay. Okay,
Yeah.
we got it. Okay, thank you.
Ma'am, we always try to take finite sample, right? When we are trying
Yeah, I mean, you
to
cannot
compute
take
the
infinite.
statistics.
You cannot take infinite, no? I mean.
But ma'am, in this one question I wanted to clarify. So when we say this X bar, I understand when as we increase the sample size, the variance would decrease because it will be centered around the mean. But I was wondering, given once we have this X bar, it will be just one number, right? And if you try to see the variance.
No. So X bar is a random variable. That is why we call X bar as a random variable, right? Because for different samples, it is taking different values of X bar, right? And that is why here I've written, suppose that my X bar now follows a normal distribution.
So we are trying to draw the graph for several
X bar. We are trying to draw the graph for X bar.
Okay, and actually it's difficult to visualize.
Yeah, all this, no, it is, you're saying it is difficult to visualize for variance of X bar.
For X bar, because when we are drawing the graph, let's say we have sample five observation, and now if I draw graph XVAR. So XVAR will be just one number for that particular data set. So I'm just trying to understand that how it would be.
Okay. So let's say you had, so this is my, let's say this is my mean, I know. Okay. Now I get some of one sample and my sample mean, let's say, come here. Okay. Then I take another sample, let's say it goes there. Take another sample, it falls there. I take another sample, let's say it falls here. Take another sample, it falls here. I take another sample, it may
When you
fall
say
there.
sample, you are referring to just one observation, right?
No,
Because
no, I am
usually
talking
sample means
no. I am talking about different instance of the samples, right? So let's say x1, x2, xn. These are IID Bernoulli. Let's say I'm taking from Bernoulli distribution only. Okay, Bernoulli P. Okay, so I am trying to find. So this is sample. This is my sample. Now I am calculating x bar. So what is my x bar? X bar will be given by x1 plus x2 plus
that
xn
part
by
is
n.
clear. What I want to understand here is when you say x1, so is it just one observation or does it include the series of observation?
Everything. So the first, let's go back to the first, very first, this thing. So let's say first I observe this sample. I calculate the sample mean for this. Again, I observe this sample. I calculate the sample mean for this, right? You keep on calculating it, right? So whatever, for different sample, you'll get different sample mean. So that is what this the sample mean I have drawn over here. You'll get here there, right?
Sets, right? For different observation.
Yeah, for different samples, you will get different sample mean, right? But all the samples are coming from the same Bernoulli P distribution. The underlying distribution is same, the Bernoulli P. All the samples are being generated from Bernoulli P distribution. Right now, for
that part is clear. Actually, what I don't understand is when we are saying this x1 to xn, right? So this xn is just one number, or does it include underlying like 5-6 values? That I'm trying
no,
to
x. Okay, so when you say capital X1, it means capital X1 is a random variable, right? So capital X1 is a random variable, and this capital X1 is coming from Bernoulli P.
Right, and therefore it can take different values, x1 itself,
right? It can
right?
take different values, yes.
Yes, okay, ma'am, thank you.
So now what will happen is, like for different samples you take, you will get different values over here, and there will be some weights associated with it, and I will get some distribution for my x bar. So what I have assumed is, let's say my sample size was good, large enough, and it follows a nice bell-shaped curve, which is normal distribution. So this curve that we have drawn here, this is for x bar, okay? And we are saying this follows a normal distribution with mean mu and variance sigma square by n. Yes, Shashwat.
Ma'am, so can we say like the x bar is the mean of the sample which we have taken from the main distribution?
X bar is the mean of the, X bar is the sample mean, correct.
So this x1 to xn is a subset of the main distribution, is it?
X1 to xn is a subset. No. This is a sample. X1 to xn is a random sample which you are taking from Bernoulli P distribution.
So each is from Bernoulli distribution.
Every random variable here, x1 is from Bernoulli P, x2 is from Bernoulli P, x3 is from Bernoulli P. Go on till xn will come from Bernoulli P, and each of these xi is a random variable.
That's why the x bar will keep changing.
That's why x bar will keep changing, because every time you generate a sample, it might take different values. Sometime I can get, if I'm talking about, let's say, just 5 sample, x1, x2, x3, x4, x5. Sometimes I can get 1, 1, 0, 1, 1. Sometimes I can get 0, 1, 0, 1, 0. Sometimes I can get 1, 0, 1, 1, 0. I mean, I can get any any sample, right?
Yes.
And that is why we are saying this sample mean will be a random variable, because I am getting at every different point of time I can get different sample, right? And if I'm getting different sample, for every sample you can calculate the sample mean. For this you'll calculate a sample mean. For this you'll calculate a sample mean. For everything you can calculate a sample mean. And this will vary. This will vary according to the samples. That is why this is a random variable. This X bar is a random variable.
Ma'am, sample and sampling are the same thing.
Sampling. So sampling, yeah, you can. Sampling is basically one particular instance of sample. So like when we are saying this, right, we have observed this. So we can say this is sampling 1. I'm calling it here sample. Like usually this is called sample, but it is actually called sampling. But everywhere you see, you will see it is the samples to be written. I mean, they will consider the sample 11010. This is one sample. It might not be called as sampling. Okay. So all of this is a sampling, if you ask me. So this is sampling 1, this is some sampling 2, this is some sampling 3. You can keep on going.
Ma'am?
Excuse me, ma'am.
Yes.
So, ma'am, basically you mean that the distribution is Bernoulli, but the X bar follows the normal distribution, is it?
No. I'm saying it may not follow normal distribution. Okay.
It's just
I'm just taking an example.
Okay.
Yeah?
Got it.
Since this X bar is a random variable, I assume that, let's say, this follows a normal distribution.
Okay.
And if it follows a normal distribution, then I know its mean would be mu, coming from here, right? Coming from this part, that mean would, expected value of X bar would be mu, and variance of X bar would be sigma square by n. So that's why I've written it here, mu and sigma square by n.
Okay, it's just an example. Okay.
It's just an example.
Okay, got it.
And what I was trying to say is that if I took a smaller sample size, you can see more spread in the distribution. If I increase the sample size, you can see less spread the data is, right? The distribution has shrunken. I'm just trying to show how with n changes your distribution will look like. I think there are various GeoGebra applets also that you can look at. Maybe you can search once. This you should be able to find. If not, we can do some illustrations on GeoGebra also.
Ma'am?
Yes. Yes, this. Bhumika, tell me.
Can you repeat the difference between sample and sampling, please?
Sample and sampling. Okay. See, this is let's say x1, x2, xn. This is sample. Okay. This is sample. We are calling this a random sample. x1, x2, xn is a random sample. Now, I can take any instance of this sample. So, if very simple example, what I'm saying is, let's take this x to be Bernoulli P. So, I can have one instance of this sample as 1, 1, 0, 1, 0, if n is equal to 5. I can have another sampling which is 0, 1, 0, 0, 1. Okay. I can have another sampling, it can go on, right? I mean, you can, every time these random variables can give you different values. So these are different samplings that you obtained at different point of time. This is sampling. And this is a random sample. Yes.
Ma'am, for these two samples, sample mean will be different, right? So,
yeah, sample mean will be different. What will the sample mean for this? 3 by 5?
Yeah.
What will the sample mean for this? 2 by 5?
Yeah.
You get some different.
Yeah, that is fine. No, I'm saying why we are using the same notation. X
Same
bar.
notation for?
The X bar will be different for sampling 1 and X bar will be different for sampling 2. How do we
No. So,
create them
okay.
differently?
Okay. So X bar is capital. This is capital X bar. Okay. So capital X bar is equal to capital X1 plus capital X2 plus up to capital Xn by n. Okay. Now all these xi's are random variable, right? And all these for different samplings, I am getting different values of xi's, right? So for each of these sampling, I can calculate a sample mean. I can call this for different, let's say for sampling 1, I can calculate the small x bar, right? And that is 3 by 5 that we got. This is also sample mean. For sampling 2, I can calculate the sample mean, which is 2 by 5.
Ma'am, I think you didn't understood my question.
Okay, can you repeat your question?
The question I'm asking is sample mean will vary by the sampling, right? So why do we use the same notation?
Same notation for?
Like how do we differentiate? Like for sampling 1, the sampling mean will be different. For sampling 2, sample mean will be different.
No. Yeah, that is what I was trying to explain. Yeah. See, x bar is a random variable. That you agree?
Yeah.
And
Yeah.
why is it a random variable? Why am I calling this as a random variable?
Because x bar will vary by the sampling.
Because x bar will vary for different samplings, right?
Yeah.
So that is why this is a random variable. Now, for each of the sampling, I can calculate my x bar, no? So if I go back to this example, so what we can do is, so this is my mu. Okay, this is the distribution mean. Now let's say I observed my sampling 1. Okay, I got the value 3 by 5 0.6. Let's say this was mu, or maybe it was 0, or maybe 0.5. Okay, it's a 0.5. First sampling, I got to be 0.6. So first the sample mean I observed to be here. Let's say in the second case, I observed the sample mean to be here. Let's say I had the another sampling, I got some 1 by 5, maybe I got the sample mean to be here, right? So fourth different sampling can come here, it can just keep on, I mean, you will get at different values of sample mean for different samples.
This 0.5 is a distribution mean, right?
This, I have assumed this is a distribution mean, yes.
Okay. So like,
you are getting confused in the notation?
No. I'm saying if the sample means are given, how do we know?
Sample means are not given, no? Sample
No,
means
for in general, like if the sample means are given, how do we get to know which sample which sample mean refers to the which sampling? Like, there should be a
no, in general,
way
like
yeah.
In general, you won't have, I mean, this is just to illustrate you that my x bar is a random variable. So in general, you will not have many samples. I mean, you can have only, and what you're saying is, if I have a sample given, how do we know this is coming from particular sampling, right? This is what you're saying, right?
Yeah, if we find the sample mean based
how
on
do we know which sampling it is coming from?
What about the reverse? Like if we are given the sampling sample means, and how do we get to know which sample mean refers to which sampling? There should be a way of representing them, right, by notation. Like,
so
yeah.
This is just to illustrate the theoretical, like how do you say it theoretically? So in general, like you will not have so many samples. You will have one sample, and you basically, we are not calling it a sampling. You will have one sample, and from that you will find the sample mean. But just to illustrate you that this x bar is a random variable, means different samples you observe, you get different values of x bar. Okay, and it follows some distribution. It has some probability distribution.
Yeah, no, the question I'm asking is like, we say expectation of x can be represented as mu subscript x, right? So that way we get to know this expectation refers to the a random variable x. So in that
Correct.
way, can we do some representation here?
So here we are. You're saying, if I'm saying, okay, you said expectation of x is mu of x. It's just for the representation that this mu is count for the random variable x. So now my random variable is x bar, right? And this, what do you want to write here?
That is what I'm asking.
But okay, theoretically we got this to be mu, right? And mu was what? Mu was just x. I mean, it is mu was for x. So still you can write this same thing, because this mu was the expectation of our distribution.
Yeah, this is the expectation of sample mean. I'm asking for individual sample means.
Individual sampling mean you will have these, no? If I give you one sample, you can always find the sample mean.
Okay.
You see, a particular sampling is not a random variable, right? If I give you just this one sample, is this a random variable? Is I calculate x bar for this sample or this sampling, which is coming out to be 0.6. Is this a random variable? No, right? This is what we had observed. And for this observed sample, we got the sample mean to be 0.6. This is no longer random, right? We had observed the sample, and using the sample, we are calculating the sample mean, which is coming out to be 0.6. This is not random. But when we are calculating this capital X bar, so when we are calculating this capital X bar, it means we are, for different samples, we are calculating our X bar, and it will give us different values, which we don't know about. So it is a random variable. This X bar is a random variable, and it will have some underlying distribution. It will have some distribution. Is it making sense?
Yeah. So
X bar will have discrete values. In this example, 3/5, 2/5, etc., right? X bar will have those discrete values, and against that there will be a probability based on the distribution, correct?
No. Can you repeat? What did you say?
So I said that, see, X bar, right? X bar will have random values. It's a random.
Which X bar you're talking about here? This one?
Capital X bar. Capital X bar will take values of 3/5, 2/5, etc., right? And it will have a probability distribution based on whatever distribution it follows, whose probability mass function will be given by the probabilities against each of those small x bars. Right?
Small x bars, correct.
Yeah.
Correct.
And is small x bar the sample mean?
Yeah, though they are also sample mean. That is for a particular sampling, you are calculating the sample mean. Both small x bar and capital X bar is sample mean. This capital X bar is a random variable, but this small x bar is a constant.
Okay, ma'am.
Okay. All right. So we were at S square. So S square is another statistic that we are talking about. We can find its expectation. So since S square is also a random variable, we can find its expectation, and it comes out to be sigma square. will not do the proof here. I think this proof has been done in one of your tutorials. Maybe you can have a look at it.
Ma'am, there are no tutorials at all. Like
For week 7?
Yeah.
There should be tutorial. No?
No, ma'am.
The week 5 tutorials in last session, ma'am had said week 5 tutorials end in, I think, second video. The third video onwards, it's actually
Yes.
week 6.
Yeah, I had to get it moved to week 6. Yeah. We'll get it done this Monday, tomorrow.
Okay, ma'am. Ma'am, in week 7, we have no tutorial videos.
Not video, I'm talking. No, I'm not talking about video. Tutorials in general.
Okay, ma'am.
Yeah.
Ma'am,
All right.
one more doubt. We need to watch additional content which was there in week 7.
Additional content, if you are interested, you can watch it. But all the additional content that is available from week 7 onwards will not be a part of your quizzes.
Okay, ma'am. Ma'am,
Yeah.
like there is no question from additional content in exam.
No question from additional question in exam. No question from additional question in assignments.
Okay, ma'am.
Ma'am, are there any more topics to be covered?
Yes. Next is sample proportion, and then next we have peak law of large number.
Ma'am, what about Chernoff's inequality?
Which Chernoff inequality?
Yes.
Yeah, that is kept under additional content.
Okay, ma'am.
Yeah, so if you're interested, you can go ahead and watch that video. And if you have any doubt, we can discuss it in the next class.
Ma'am, how do we prove this? We have to use the estimators.
No, you don't have to use estimate. You just have to use the definitions. So S square is this. You just have to break this term. So xi minus x bar square, you have to split this. It will be what? Xi square plus x bar square minus 2xi x bar. So write every term and just do some manipulation. Not very big proof, a small proof. Just try it out. Okay, so next we have sample proportion. So again, we have the same setup. We have x1, x2, xn, iidx. And now we are defining an event A. So this is an event A using x. Okay, so using this distribution x. So you can define it in any way, right? You can maybe call the event A is defined as x lies between some A and B, or x lies between something, or maybe x is greater than A, or maybe x is less than B, or x is equal to B. You can define event in any way using x, right? So you have some IID samples coming from the distribution x. You have some event defined using x. Now the sample proportion, what it says is, so sample proportion of this event A, which we denote it as capital S of A, this is equal to number of times for which xi Um, so S of A is equal to, okay, number of times number of xi's for which A is true. Divided by n. So for example, if I go to the same Bernoulli example, I have suppose a sample which is 0, 1, 0, 1, 1. I define an event A which says my event says x is equal to 1. Okay, this is my event. Now what is going to be S of A using this definition? This is going to be number of xi's for which x is equal to 1, right? For which A is 2 means number of xi's for which x is equal to 1. So we have to find, so how many sorry, so how many xi's are equal to 1? That is 3, right? So it will be 3 upon 5. If I suppose if I have some other sample and maybe take some value 2, 3, 5, minus 2, minus 2.50. Okay, this is suppose one sample. Now I define my event A as my x to be maybe greater than maybe 5, maybe 3. Okay, x greater than 3. This is one event that I define. Now what is going to be the sample proportion of A? This is going to be number of times for which xi is greater than 3. So this is only one xi for which this is 2. So this is going to be 1 upon 6, right? So you are getting.
So it means the sample proportion and the empirical distribution, they are the same thing?
Yeah, more or less it's the same thing, yes. So there, no, not exactly. So there in empirical distribution, what we are trying to do is, if we are given a sample, so if this sample was given, I know it is given to us that there is 0 and 1. So in empirical distribution, what we did is we counted how many times 0 has occurred in the sample, which is 2 upon 5. How many times 1 has occurred in the sample? 3, and the probability was 2 upon 5. This was the empirical distribution. But here we are okay. If in the second question, if so, what all values do you have in the sample? You have 1, you have 2, 3, 5, minus 2, minus 2.50. You have 6 values, and all of them are occurring only once, right? If you go back to the empirical distribution definition, what did it say? Number of times t appears in the sample divided by n. So if we have to find maybe p of 2, so how many times did it appear in the sample? Only one time. That is 1 divided by total number of sample, which is 6. So 1 upon 6. Right? This is empirical distribution. I mean, you will do it for all the values that you are seeing in the sample. But you're getting the idea, right?
But sample proportion, I mean, it is also the same thing because we are doing in the same manner.
No, in this case, we are defining particular events. So we are defining an event which is x. So for this example, we define the event as x greater than 3. I can also define, let's say, x lies between 3 and 0. Okay, I can define this event. Then I can also find the sample proportion for this. And this is what? This is equal to number of times. So how many xi's lie between 0 to 3, right? So it is going to be just 1, which is only 2 lies between 0 to 3, right? So again, 1 upon 6. Where empirical distribution, you are finding for particular value that occur in the sample, right?
Okay, okay.
But here you are.
Ma'am, but in the above example, It is same as empirical distribution now.
Yeah, but okay, now I can define another event. Let's say I define an event which is x is greater than 0. Okay, then what is S of A going to be? Can you tell me?
3
This,
by
Ma'am,
5.
5.
In this case, it is coming to be same, but okay, let's say x is equal to, let's say I say define x is equal to 0.5, then what will happen? What is S of A?
0.
0, right? So it depends on what event you define on x. Sample proportion you are finding for the events. S of A, sample proportion of the event A. Correct?
Yes, ma'am.
So this is how we find the sample proportion. Now, again, this was another statistic. So first statistic, we look at sample mean, then sample variance, and the last was sample proportion. And again, we can write its expected value. So expected value of S of A, expected value of S of A is nothing but probability of A, and variance of S of A can be written as probability of A times 1 minus probability of A divided by N. This is the expectation and variance of the sample proportion.
Ma'am, these formulas were given in exam.
These formulas will not be given in exam.
Okay, ma'am.
And the last formula you have written, variance of S of A, it corresponds somewhat looks similar to variance of Bernoulli.
This right?
Yes, ma'am.
This is nothing but variance of a Bernoulli distribution. So if I call P of A, so this P of A is nothing but what? Maybe if I can write, let's say P of A is some P. Because what I am basically saying is, if I'm defining an event, I'm just seeing whether x is greater than 3 or whether x is between 0 and 3, right? So I check for different values of samples and I say either yes or no. So if I define my event as x greater than 3, so what I'm saying is, I will go to the first sample. This is 2. This is not greater than 3, right? So this will take the value 0. If I'm looking at 3, again, this is not greater than 3. So again, this will take the value 0. If this is 5, it is greater than 3. So it will take a value 1. Everything else is taking the value 0 because it is all less than 3. So it is kind of, this event is kind of giving you a Bernoulli distribution, right? And if I can define this P of A, probability of this event to be P, so this P is nothing but this Bernoulli, this is a Bernoulli distribution, right? The probability of A is this P.
Ma'am, what is the logic behind dividing with N?
Logic behind dividing by N, right? So, okay. This is, okay. The top part follows the Bernoulli distribution, right? So even when we looked at sample mean, it was x1 plus x2 plus xn by n. So in SA, in sample proportion, you again have number of xi's for which ai is 2 divided by n. So here also you are dividing it by n, and when you find the variance, so When you find the variance again, it will get cancelled out, I think. So you will get again sigma square by n kind of. You get sigma square by n. And this is mu.
Okay, so this P of A times 1 minus P of A is for the variance of the the distribution.
The variance of
The
the Bernoulli.
distribution.
Yeah.
Okay, so that's why we are dividing with
Ma'am, are you telling something?
No, I'm not telling anything.
Ma'am, how many topics are there in week 7?
Yeah, there are 2 more topics actually left. So one is expected value and variance. Another is weak law of large number. So weak law of large number is nothing but Chebyshev inequality, so it should not take much time. We can go to expected value and variance.
Weak law is given in assignment, graded assignment.
Yeah, weak law. Yeah, it will be there in graded assignment, no? Week 7.
You told it's additional, so as.
No, weak law of large number is not additional. Chernoff bound is additional.
Okay.
Yeah. So, okay. Now let's consider the case where x1, x2 up to xn, they are coming from distribution x. We are not saying if they are IID or not. Okay, we don't know if they are IID. Now we are defining another random variable s, which is equal to okay. So we are defining another random variable s, which is equal to sum of all these random variables. Now, if I have to find the expected value of this s, then it will be equal to what? Since expectation follows the linearity property, I can just write this as expected value of x1, so on till expected value of xn. But can we do the same thing for variance of s? Can we write variance of s as variance of x1 plus variance of x2 plus up to variance of xn? Can we do that?
No, ma'am.
Yeah, if it is
No.
independent.
If it is independent, then we can do it. So if all these x's are independent, then we can do it. Or another way to say is like if all these, so we'll write variance of s is equal to variance of x1 plus up to variance of xn if xi's are pairwise uncorrelated or they are independent. Pairwise uncorrelated. So when we say pairwise uncorrelated, we mean that expected value of any two random variable, that is expected value of some xi, xj is equal to expected value of xi, expected value of xj for all ij where I is not equal to j. So if this happens, then we can write variance of s to be individual sum of all the variances.
Ma'am,
Hmm.
ma'am, pairwise uncorrelated, make sure it is independent. Because if it is independent, we say it is uncorrelated. But the
If it
converse
is
is not always true.
if it is independent, we say uncorrelated, right? Independent.
Yeah.
See,
And the converse is
if
not always
converse
true.
is not true, if you have x's to be independent, then we say they are uncorrelated, right? But the converse is not true. Uncorrelated does not imply independent. So yeah, if if x's are pairwise uncorrelated, or we can also say if x's are uncorrelated, then we can write variance of s to be variance of x1 plus up to variance of xn.
So if they are uncorrelated, there may be a few data points related.
Few data points related means?
I mean, if they are uncorrelated, that doesn't make sure
all are independent.
All are independent.
Yeah, it may not be true.
There may be a few data points that are related.
Ma'am, if x's are pairwise uncorrelated, then how we can say variance of s is we can write variance of x1 plus up to variance of xn.
No, I couldn't hear you. Can you repeat? Voice is breaking a little.
Ma'am, if x's are pairwise uncorrelated, then how we can write variance of s is equal to variance of x1 plus up to variance
Proof.
of x.
Yeah, proof I have not done. It has been done in lecture. I would request you to please just go over it and see like why we are able to say that if these x's are pairwise uncorrelated, then variance of s is sum of the variances.
Ma'am, but if they are pairwise uncorrelated, then it can be dependent. So, ma'am, how we can write it
So
is not.
okay, so if x's are independent, if your x's are independent, we also say that they are uncorrelated, right?
Yes, ma'am.
So in that case also we can say no that variance of, I mean, if your x's are independent, then also this is equal to sum of this. We can say that because
But in
xi
some,
independent
but in some
implies uncorrelated.
I said, but in some dependent case, I mean, also this can be true if they are pairwise uncorrelated.
Yes, ma'am.
No, we are not saying that uncorrelated implies independent. We are not saying that. We are saying if x's are independent, then they are uncorrelated. This we know. Okay. So
But
if
I
A
said, I mean,
implies,
this can be. I said this can be true for some dependent case also, when they are pairwise uncorrelated. In dependent case.
okay. Can you repeat your question again? Think.
I said that this can be, I mean, true for some dependent case also, when they are pairwise uncorrelated.
If they are pairwise uncorrelated, yes. Yes.
Okay.
So see, A implies B, right? If A implies B, and we are saying this B implies this, so A implies will also imply C, no? If xi's are independent, this is okay, right? If even if xi's are independent, we'll say that this is variance of S is equal to sum of these individual variances. This is fine, even for independent case.
Yeah, ma'am, it's clear.
Okay. Alright, so next that we have is some properties which, okay, I'll just write it. Maybe we can look at it. Next, the last topic that we have is weak law of large number. So weak law of large number is nothing but Chebyshev inequality. So this is nothing but your Chebyshev inequality. So what does weak law of large number says is, suppose you have x1, x2, xn, IIDx. Okay, you have n IID samples, and suppose expectation of x is given to you as mu, and variance of x is given to you as sigma square. Right? Now, the weak law of large number says that probability that my mod of x bar minus of mu greater than delta is nothing but less than equal to variance of x bar divided by delta square. And this is nothing but our Chebyshev inequality. Even in Chebyshev inequality, we are doing the same thing. We had a random variable. We said probability that mod of x minus expectation of x greater than some constant delta will be less than equal to variance of x upon delta square. So this just x is replaced by x bar. So what we had, where we had just one random variable, we are talking about Chebyshev inequality. Now we have n IID random variables, n IID samples, and now we are talking about the distribution of sample mean. Now we are talking about x bar, not x. We are talking about x bar now. That's all. That's all the Chebyshev inequality is. So this gives you the bound on the probability. Like, what is the bound on the probability that x bar will be away from mu by some delta? Delta can be some very small value, right? So if this is my mu, right? This is my some delta. This is some delta distance. So this will be mu minus mu plus delta. Mu plus delta. This will be mu minus delta. So what is the probability? What exactly it is saying is, what is the probability that my sample mean will lie outside this interval? This interval will lie outside this. What bound can you give on that probability? This is called weak law of large number. And if we change the inequality, what can we say? We can say that probability that mod of x bar minus of mu less than delta will be greater than equal to 1 minus variance of x square by delta square. And what do we know? That we know that variance of my x bar is nothing but sigma square by n. So I can write this as sigma square by n delta square. I can write this as sigma square by n delta square. Right? And what will this probability give? This will give the bound on the probability that x bar lies inside this interval. So that bound will be greater than equal to this value. Is this clear?
Yes, ma'am.
Yes, ma'am.
Okay. Yeah, that's all. That we don't have any other topic left in week 7.
So we have this much topic. I mean, only in week 7.
Yes.
My inferential part will be from week 9.
Week 9, yeah. Like week 7, it will just build the foundation, and then
The foundation means
week 7, week 8, your CLT and everything will start from week 8. Mostly week 9 estimation will start from week 9. Estimation and hypothesis testing. Just Disha.
Ma'am, I have a doubt in activity 7.2, question number 6.
Activity, yeah, thank you. Activity 7.2.
Question number 6, ma'am. Ma'am, ma'am, you are not audible.
I was not audible to anyone.
No, ma'am.
No,
Ma'am, you
ma'am.
can.
Okay. Okay. So what I was saying is, here in this question, it is given to you that a certain type of thread is manufactured where the mean is given to you as 65 kilogram and standard deviation is 6 kilogram. Now now what we have to check is how the variance of the sample mean will change. So first we are taking the size from size as 100, and we are increasing the size to sample size to 256. So we have first, let's say, sample size to be 100 and N2 to be 256. Okay. So what we want is how the variance of X bar will change. So what is variance of X bar? It is sigma square by N. And what is sigma square given to us in the question? What is sigma square given to us in the question? 6 kilogram. Sigma square will be, sorry, 6 square.
Ma'am, it's sigma na. Standard deviation is given, not variance.
That's why I written 6 square.
Okay, ma'am.
Okay. Now when you take N1 to be 100, what will happen? You will get, in this case, 36 by 100, and in this case you will get 256 by, sorry, 36 by
36 by 256.
256. So just calculate the value. It is obvious that the variance would decrease because my sample size is increasing. right? If my sample size is increasing from 100 to 256, the variance would reduce, which is reducing here. You can see 36 by 100 and is going to 36 by 256. Just calculate the value and see what is happening. What value are you getting?
Okay, ma'am. If sample size is decreasing, then our variance is increasing, like that, ma'am?
Yes, of course.
Okay, ma'am.
Excuse me, ma'am.
Yes.
Could you take question from week 6 GA?
Week 6 GA. So as I said at the starting of the session, we'll conduct one more session for week to take doubts for week 5, 6. Many students seem to have some questions. So we'll schedule one separate session for week 5, 6.
Okay.
Okay, then let's close the session for today.
Thank you, ma'am.
Yeah, thank you.
Thank you, ma'am.
Thank you.
Good night, ma'am.
Good night.
Thank you, ma'am. Bye. Good night.
Thank you.